Okay. Thank you for invitation. I would thank Xiaoliang and Steve and other organizers to organize this wonderful memorial workshop for Shoucheng. So, I would like to talk about our work, which is closely related to Shoucheng. This is not a very hot topic. It's actually it's not a cold. It's actually quite a cold topic. So the good point is that nobody compete with us, so that we can do it slowly. So this project actually was done by my student Zhang and Sun Song and my long-term collaborator Zhang from IOP, and myself has recently moved to Hong Kong University of Science and Technology. So I would like to first of all mention a little bit about the Shoucheng, how Shoucheng inspired me to this field, to working in this field of topological materials. So actually, Shoucheng is for me, he's a great scientist, great mentor, and a great pioneer in our field of topological material. So me and Zhongfang, we have several quite important papers with Shoucheng, and I think we are trying to just find in real materials lots of these beautiful topological features in the band structure. So among those papers, I think Xiaoliang has mentioned several of them, including the three-dimensional topological insulator and the quantum anomalous Hall effect. All these works are collaborated with Shoucheng and with his great insight and the great contribution on the theory. And in today's talk, I'm going to focus on a very small part of the topological material. It's the G factor. So this work is closely related to, I remember that there was a global meeting like 12 years ago here in Stanford, because I still remember that during that time, I was visiting Shoucheng's group for like 2 or 3 weeks. So during that time, I attended one of his group meeting, and one of his students gave a summary, because Shoucheng asked the student to do some literature search on the G factor in solid state physics. So before this group meeting, I saw G factor was just some number which is determined by some experimental measurement, and it can be different from material to material, but I didn't think so much about what's the physics behind. So it's during this global meeting, and we discussed what's the physical origin of the G factor. So basically, it's the screening of the current. We can make a comparison with the dielectric constant. So the dielectron constant is responsible for the screening of charge. So this G factor is basically screening of current. So then we realized that in solid state physics, for many systems, once we have both time reversal symmetry and inversion symmetry, the band has always a double degenerate. But then once you turn on the magnetic field, the magnetic field has two effects. The Landau level effects, the orbital effects, which forms Landau level, and the Zeeman effect, which split these two bands. So then we realized that this G factor is k-dependent. It's G factor is in solid states is defined always in momentum space. So in most of the cases of semiconductor, we are only interested in a small area of Brane zone near for example, gamma point. So we focused on the G factor at the gamma point. But in general, G factor is a k-dependent object. Then Shoucheng just conclude that the k-dependence of G factor can be very interesting. Maybe for some very special material, the G factor itself, because it's k-dependent, it's a 2x2 matrix for these two bands. So maybe someday we can find some very special material. This G factor itself has some topological structure because it's a 2x2 matrix. It behaves just like a Hamiltonian. So if you can define the topological structure for Hamiltonian, you can define the similar topological structure for G factor. Then Shoucheng probably already forgot what he said, but I keep this in mind. And then during our research of topological insulator, we try to calculate the G factor of topological surface data for a three-dimensional topological insulator. Then we find that computationally this is not so easy for surface states. So then we got the motivation to develop some first principle tool to do the computation of G factor for real materials. So here is a little bit of the outline. So I will introduce to you how to calculate the G factor from first principle. So, and I will give you some examples of why the G factor is so important to determine lots of properties of topological materials on their magnetic field. So I think I've already mentioned there are two effects of external magnetic field, the Zeeman effect and the Landau level quantization. So then how to distinguish these two effects? So basically, if you turn on the external magnetic field, can be modeled by a vector potential A. So the vector potential A has two contributions, the intraband contribution and the interband contribution. So the intraband contribution gave us the Landau level quantization, and then the interband components actually give us the G facts. So in order to do that, first of all, we need to separate our energy bands into two subgroups, the low energy and the high energy subspaces. So and the G factor can be only defined in the low energy subspace where its screening is from the high energy bands. So and G factor is very important for the topological material. For example, for three-dimensional topological insulators, if you want to determine the surface property once you turn on the magnetic field, the G factor is very crucial. And the second example is for topological semimetals. Some of the topological semimetals, like the Dirac semimetals, there are two energy bands cross right at the Fermi level, so they are doubly degenerate. Once you turn on the Zeeman effect, you are going to split these Dirac point into some wild points. But then how they split, it's closely related to the G factor tensor. So I will show you an example. So the G factor can be understood starting from the Dirac equation. By Dirac equation, I mean the Dirac equation for free electrons in vacuum. So in Dirac equation, there's no G factor. There is only a vector potential A, right? So it's a 4x4 Hamiltonian. So then our solid state physicists, we only interested in this upper band of the electron band near the gamma point, let's see, near K, about K equal to 0. So then the first we do is that we downfold this 4x4 Dirac equation to 2x2 Shoucheng equation with some correction. So with the external magnetic field, there are actually two kinds of correction. One is, of course, spin orbital coupling. The other one is the Zeeman effect, described by the G factor. But here, because we're only interested in the states near k equal to 0, which is emphasized by this black regime, in this regime, the k dependence of G factor is very weak. We can neglect the k dependence. So we can treat the G factor as a constant for electron moving in the vacuum. So only if you move to a very high energy regime, for example, this red regime, where the speed of the electron is close to the speed of light, in this regime, the G factor tensor will get a very strong k dependence. But for our solid state physics, we only live here. So the original, I would say, original G factor for solid states is not k dependent. Is simply G equals to 2, right? For a spin 1/2 system. But then we come to these energy bands. So once we turn on this periodical potential, and for example, we've applied this LDA approximation, and we calculate the energy bands. So if you put G factor G0 equals to 2, you need to keep all the high energy bands. So for example, we usually we take like 100, 200 energy bands to describe the full picture of the electronic structure of one particular real material. But then if you keep all those bands and you keep all the interband components of the vector potential A, so that gives you like complete description of the external magnetic field for this particular material. But then this, of course, is not convenient. So the convenient way is we try to downfold this full Hamiltonian into some low energy effective Hamiltonian, which we only include several different bands. For example, if the system has an energy gap and we only interested in the low energy state near the Fermi level, we need to downfold it into just the lowest two bands, which is degenerate without a magnetic field, right? So during the downfolding process, this G factor got strongly renormalized because there is matrix elements of the vector potential in between two different bands among like a high energy band and the low energy bands. So this is the origin of the renormalization of G factor. So let's make a long story short. So this is the typical K dot P Hamiltonian for a real material. So once you downfold your full Hamiltonian into the low energy subspace, you will get a contribution like this. So this is the downfolding without external magnetic field. You don't have a vector potential A. So without a magnetic field, you get a correction like the effective mass correction. So this is standard. But then once you turn on vector potential A, you will get some additional terms. Then you will get two contributions from the vector potential A. One is, we call it a symmetrical combination of this A vector. And this symmetrical combination gives you still the correction, the intraband terms. It describes the formation of lambda level. But there is another anti-symmetric combination of the vector A and this partial operator. So that gives you these terms, which is exactly the normalized, renormalized Zeeman effect. So in addition to bare spin operator S, there is an orbital angular momentum contribution from the high energy bands. We call it L. So combine these two, we can extract the G-factor tensor from this L operator and the S operator. So then we know that in order to compute this L operator, L operator is nothing but some complicated combination of this pi operator is nothing but the momentum operator in the language of energy bands. In terms of the energy bands, here the M is the energy bands in the low energy subspace, and those L is the energy bands. M is in the low energy subspace, and L is in the high energy subspace. So the only thing we need to know from the first principle is this standard momentum operator, the matrix element of the momentum operator in the band basis. So then using the pseudo-potential method, we can compute these matrix elements, and we can develop a first principle method to calculate the G-factor for real material. So we tested our code on to calculate the G-factor of bismuth and three-dimensional topological insulated bismuth 2793, and we get these numbers. And to get a good agreement with the experiment, we need to apply this MBJ functional, which actually can get the size of the energy gap right. So here we learned that in order to get the reliable G-factor estimation, you need to first get the energy band of the semiconductor system right. Then you will get very good comparison with our calculation and experiments. So then another example is the Dirac semi-metal sodium bismuth. So in this material, we have along the z direction, there's a two-band cross very close to the Fermi level, form a Dirac point. So this is a real band structure. You can see this the crossing here along the gamma point to the z point, and we calculate the G-factor tensor within this 4x4 low energy subspace. So the G-factor tensor here is also a 4x4 matrices, and we got these numbers. You can see that the G-factor is pretty big along this parallel to the z direction. And then, it has quite strong anisotropic behavior. And so we put this first principle G-factor tensor to calculate the phase diagram of sodium bismuth, a typical Dirac semi-metal system. And we got a phase diagram like this. So you see this horizontal axis is the magnetic field along the B direction, and the y-axis is the magnetic field along the Z direction. So by changing the strength of the Bx and Bz is actually changing the field direction. So you will see that by changing these two parameters, and you will get a very fruitful phase diagram for this Dirac semi-metal system. So before we apply the magnetic field, the system has a small has non-zero chemical potential. That is to say, the chemical potential is not exactly across the Dirac point. So then what the Zeeman effect does is to split these two wild points, because before they sit on top of each other. Now the Zeeman effect shift away these two Zeeman wire points and to form such a fruitful phase diagram. For example, in this phase, in this phase 1 prime, the Fermi surface will, these two wire points will shift in such a way that they are going to form two Fermi surfaces, two small Fermi pockets. One is electron-like and the other one is Hall-like, and the electron-like Fermi surface has a total, actually, Chern number -2, and the Hall-like Fermi surface has a total Chern number +2. And for this phase, it's also split into one electron pocket and one Hall pocket, but the Chern number is -1 and +1, and also these other three different other phases. So another example of how G-factor changed the property of the material is the G-factor is very important for quantum oscillation. So if a system has a doubly degenerate Fermi surface, once you turn on magnetic field, the Zeeman effect does two effects. First of all, it splits the Fermi surface into two Fermi surfaces with different area. So then it should contribute to two frequency to quantum oscillation. But secondly, once it split the Fermi surface, it also split the Barry curvature. Because before, the Barry curvature of a two-fold degenerate Fermi surface is non-abelian. It's a 2 by 2 matrix. Once you split it into two, 1 by 1, the Barry curvature becomes just U1 object with ordinary, just become ordinary band structure, Barry curvature. So then at extreme circle of that Fermi surface, the Barry curvature also split into two numbers. One is here. One is plus theta and one is minus theta on that particular extreme circle. So combine this Fermi surface area splitting and the Barry curvature splitting, you have to combine these two effects to determine the right behavior of the quantum oscillation. So because this two frequency, because you split Fermi surface into two, you got two frequency. So in quantum oscillation, you got two cosine terms add up together. So you end up with just a phase factor in front of the ordinary the quantum oscillation phase determined for non-magnetic, without considering the Zeeman effect. So the Zeeman effect is just contribute to a phase factor here. So then this alpha is the effective G factor along that particular direction. So then we know that if the phase factor inside this cosine is equals to pi times 2n plus 1 over 2. For example, equals to pi over 2, then the whole quantum oscillation will vanish. The system has no quantum oscillation along that particular angle of the magnetic field. So then this effect is, in the textbook, is called spin zero effect. So then for a system with very strong spin orbital coupling, the spin zero effect has to be determined by both the effective G factor and the effective Barry curvature splitting on that Fermi surface. So we, in our numerical calculation, we include both effects, and we calculate the spin zero angle for zirconium telluride 5. So then we get our theoretical prediction for the angle to have spin zero effect for this particular material. We predict the two angles. One is if the magnetic field is within the BC plane, our theoretical prediction of the spin zero angle is about 75.6 degree, which is quite consistent with the experimental result about 83 degree. So then along another direction, which is in the plane between A and B, so this angle become 83 something, and the experimental angle is 86. So you see very close. So we also tested if we don't include the contribution from Berry curvature splitting, this angle is completely wrong, cannot compare to the experimental data. So another very interesting phenomena of the GFACT, of course, is as I mentioned, is the topological nature of the GFACT itself. If the GFACT has a very strong K dependence, it can split Fermi surface into two. Then after splitting, each of the Fermi surface will carry a Chen number. So, so this is a material we found is titanium arsenate 2. So we know that titanium arsenate 1 is a very good wild cell metal. So this guy is made by mistake, because I asked my colleague in IOP, please grow titanium arsenic, and they growed some sample and find out it's not 1-to-1 sample, it's 1-to-2. Then they measured the transport. They also see very beautiful negative magnetoresistance. So then the guy just come to my office, say, okay, what happened? So they finally they grow both 1-to-1 and 1-to-2 sample, and they compare the negative resistance, and they see the comparison is very good. So they look very similar. So, but from the band structure. So this is the band structure of the material. It's some we call it trivial semi-metal system, because there's overlapping some energy band, but there's no wild point at all, because we have checked because the system has both inversion symmetry and time reversal symmetry. There's no way you can have a wild point in the brane zone. So the Fermi surface contains many like small Fermi pockets, and they are all has twofold degeneracy. So once we then we compute the GFACT on each K point of the Fermi surface. We split the Fermi surface. After splitting, we calculate its Chen number, and we found that for some two different Fermi surfaces along some specific field direction, the field will split the Fermi surface into two parts, and each Fermi surface will carry non-zero Chen number. So that we call the Zeeman effect induced topological metal phase in this material. And yeah, so here is the conclusion. My time is about. I'm ready for the question. Thank you.
Time for questions.
Concerning the last part with
Yeah.
tantalum arsenic 2, this could mean that all the also Wisinger version symmetry semi-metals can become Y semi-metal if they are heavy and if the Zeeman splitting and the G factor.
Yeah, so this result actually implies that lots of material we thought they are completely trivial. They're probably not trivial, because if you this TAAS2 for this material, if you compute any like topological invariance without a magnetic field, it's trivial. So it seems to be a very.
100% topological materials.
Sorry?
You have 100% topological.
Yeah. So, but then if you consider the Zeeman effect, the Zeeman effect will split the Fermi surface into two. Each of the Fermi surface carries a non-zero Chen number. So then the material is no longer trivial on the magnetic field. Yeah.
Do you have examples of G factors
the question is recorded, so
Sorry,
please use the microphone.
So say I have different Fermi surfaces in different parts of the Brion zone.
Could you repeat the question?
Say I have different Fermi surfaces in different parts
Right.
of the Brion zone at different high symmetry momenta. Can I
Yeah.
have different G factors for each of those Fermi surfaces?
Yes, very, very different. So for example, for this tantalum arsenic 2, we calculate the 3 different Fermi surfaces. Because if you look at the Fermi surface distribution, there are basically four different type of Fermi surfaces. And my student just finished the 3. There's another one is still he's working on that. So then we found 2 of them topological non-trivial because the G-fact tensor is very different. But because it's different from point to point, you have to calculate the G-fact tensor on each k point of the Fermi surface in order to determine its Chen number.
And that's because of the G factor, not because of the Fermi surface, really.
Yes. It's because, no. It's the combination of both. Because the G factor has such a topological structure there. But if you want to see some measurable quantity, so then you have to put a Fermi surface there. So the material has to put a Fermi surface on that area where the G factor is non-trivial, right? Yeah.
So if you have a material like this and applying magnetic field, like, is it dominated by Zeeman effect or orbital effect?
Yeah, that's a very good question. Yeah, I forgot to mention that this is, of course, an approximation. So the approximation is the G factor, the amplitude of the G factor is so big that the energy of the Zeeman splitting is several times bigger than the cyclotron energy of the lambda level. Yeah, but we found that this assumption is generally true for most of the topological and for most of the material with very strong spin orbital coupling. The G factor is around 6 to 10. So yeah, it's kind of can be satisfied for many materials.
Yeah, thank you.
Because you have to neglect the after Zeeman splitting this two-fold degenerate band split into 2 one-fold. So in our approximation, we basically neglect the matrix element of the A vector between these 2 splitted bands. We only keep the U1 part. Yeah.
Any other questions or comments? No? Okay, if not, then let's thank the speaker again.
Yeah, thank you.
A lunch break. And I think the afternoon session will start from 2 p.m.